In determining at what point and how much force to exert on a man-made satellite to change its path, the engineers need to calculate such quantities as the slope, the tangent line, and the normal to a curve, as well as the rates of change. Hi, my name is Tom Atwater, and that's what we'll be visiting in today's lesson. Let's get started with looking at the average rate of change. Find the average rate of change of the function f of x equals e to the x over each time interval. For part A, it's -2 to 0, and for part B, it's 1, 3. Now, the average rate of change of a quantity over a period of time is the amount of change divided by the time it takes. So let's do that calculation right here. We would have that the rate of change will equal e to the 0 minus e raised to the -2 over 0 minus -2. And then that would be equal to, well, e to the 0 is just 1 minus e to the -2 over, and 0 minus the -2 is +2. So that's the average rate of change over the interval -2 to 0. Let's do it for 1, 3. We would have e to the 3 minus e to the 1 over 3 minus 1. And that's going to equal e to the 3 minus e over 3 minus 1, which is 2. And that would be the average rate of change over the second interval. Now, we start with this idea and work with it to find the tangent to a curve at a certain point. Here's a description of what we can do. To find a tangent to a curve, we start with what we can calculate, namely the slope of a secant through P and a point Q nearby on the curve. Then we find the limiting value of the secant slope, if it exists, as Q approaches P along the curve. And then we define the slope of the curve at P to be this number, and define the tangent to the curve at P to be the line through P with this slope. More formally, we can define the slope of a tangent line in the following manner. The slope of the curve y equals f of x at the point P, which is equal to a comma f of a, is the number m, which is the slope, equaling the limit as h approaches 0 of f of a plus h minus f of a, all divided by h, provided that that limit exists. Let's look at an example of where we apply this formula. Let f of x equal 1 over x. Find the slope of the curve at x equals a. Then, where does the slope equal -1/4? And what happens to the tangent of the curve at that point a comma 1 over a for different values of a? So the first thing we need to do is apply that formula. So we need to write out the limit as h goes to 0 of f of a plus h minus f of a over h. And now use the function f of x equals 1 over x and substitute those values. So what we have is equaling 1 over a plus h minus 1 over a, and that's all over h. Then we can simplify that to 1 over h times a minus parentheses a plus h over a times a plus h. Continuing along, we can simplify the top of this. We'd have 1 over h times negative h over a times the quantity a plus h. Of course, these cancel, leaving us negative 1 on the top there, which we can continue to simplify. And we get negative 1 over a times a plus h equals, and, well, we can multiply this out on the denominator, a squared plus ah, and see now that the limit as h goes to 0, right here, of course, as h goes to 0, a times h will go to 0, and that means this limit is negative 1 over a squared. So that gives us the slope in general for some value of a. Now, what we were asked is, when will this slope actually equal negative 1/4? So what we do is we will set up the problem, negative 1 over a squared equals negative 1/4. And of course, that will lead to the answers a equals plus or minus 2. So those are the values for which we get a slope of negative 1/4. Well, what that means is, first of all, we know that the slope is always going to be negative because we came up with negative 1 over a squared, and a squared is always going to be positive. So negative 1 over a squared is always going to be negative. Now, the slope will therefore approach negative infinity because as we approach values of a, going to 0 from the positive side, it will go to negative infinity. But as we approach it from the negative side, it'll also go to negative infinity. Now, as we move away from the origin, the slope of the line will approach 0. And so the tangent line becomes increasingly horizontal. Okay, now the normal line to a curve at a point is the line that's perpendicular to the tangent at that same point. So now let's look at finding a normal line. For y equals x squared at x equals negative 2, find the slope of the curve, find the equation of the tangent and the equation of the normal, then draw a graph of the curve, the tangent line, and the normal line all in the same viewing window. So what that means is we need to apply that same formula for the slope. In other words, the slope is the limit as h goes to 0 of, and we were given the value x equals 2, so it's going to be x equals negative 2 plus h minus f of negative 2 over h. And our function this time is x squared, so this is going to be equal to negative 2 plus h quantity squared minus negative 2 squared all over h. Simplifying this, we get 4 minus 4h plus h squared minus 4 all over h. Simplifying further, of course, the 4 minus 4 goes to 0. I can factor an h out, and I will have h times minus 4 plus h all over h. Those h's cancel out. We're left with minus 4 plus h. Of course, as this h goes to 0, this limit goes to -4. So what that tells us is the slope of the tangent at the point x equals -2 is -4. So the equation for the tangent line would be the y equals -4 times x plus, of course, we don't know what the y-intercept is. But what we do know is that when x is equal to -2, y would be equal to 4 because the function is y equals x squared. So we can plug that in. 4 equals -4 times -2 plus b. That will give us an answer of b is equal to -4, so that I can substitute in, and our equation for the tangent is y equals -4 x minus 4. The next thing we were asked to find was the equation for the normal to the curve at that same point x equals -2. Now remember, the normal is perpendicular to the tangent, which means the slope of the normal is going to be the negative reciprocal of this slope, which means it's the slope 1/4. Okay, so I need some more space here, so let me erase what I have here. And we know that the normal would be y equals 1/4 x plus b. And once again, we use the same point, -2, 4. And we get 4 equals 1/4 of -2 plus b. So this is 4 equals -1/2 plus b. So b is going to be equal to 4.5 or 9/2. So the equation for the normal is y equals 1/4 x plus 9/2. And that's a linear equation for our normal. So the last part of this particular problem is to draw the graph that shows the tangent line, the normal line, and the curve itself. So let's do that. Plugging it into our calculator and graphing it gives us y equals x squared, which is the parabola. The tangent line is very close to it, but it's this line right here with the -4 slope. And then the normal is this line right here, which has a slope of 1/4. All right, great. Now, one of the applications of this is to speed. So let's look at an application of a free-falling rock. A rock breaks loose from the top of a tall cliff and falls 16 t² feet after t seconds. How fast is it falling 1 second after it starts to fall? So again, what we're going to do is apply that formula for this particular problem. So what we have is the limit as h goes to 0 of f of 1 plus h minus f of 1 all over h. And the function that we're dealing with is 16t². So this would be equal to 16, 1 plus h quantity squared minus 16 times 1 squared all over h. And now let me move on to another screen where we can continue simplifying this. So we would have that it's equal to 16 times 1 plus 2h plus h squared minus 16 all over h. That's going to be equal to 16 plus 32h plus 16h squared minus 16 all over h. 16 minus 16 gives us 0. I can factor an h out of both 32h, which leaves me with 32, plus 16h all over h. The h's cancel to 1, and so I'm left with 32 plus 16h. Now, as h goes to 0, 16 times h goes to 0, and that means that the limit as h goes to 0 is 32. So that free-falling rock was falling at 32 feet per second. Now it's time for you to try a problem. Free-falling, an object is dropped from the top of a 100-meter tower. Its height above the ground after t seconds is 100 minus 4.9 t squared meters. How fast is it falling 2 seconds after it is dropped? Pause the video while you work on this problem, and when you are finished, restart the video to check your solution. All right, so we have to apply that same formula to the problem that I gave you. So what we're looking for is the limit as h goes to 0 of f of 2 plus h minus f of 2 over h. The formula I gave you was 100 minus 4.9 times t squared. So what we have is 100 minus 4.9, the quantity 2 plus h squared, minus the quantity 100 minus 4.9 times 2 squared, all over h. All righty. So now let's look at simplifying that. So let me go to a clean screen and continue with this problem. We have that that's going to equal 100 minus 4.9 times 4 plus 4h plus h squared minus 100 plus 19.6 all over h. And that's going to equal, we've got to distribute out the minus 4.9, and I can at least say 100 minus 100 will give us 0. But then what we have is negative 19.6 minus 19.6h minus 4.9h squared plus 19.6 all over h. We can take the 19.6 minus the 19.6, and of course those go to 0. I can factor out an h from each of these, and I get h times negative 19.6 minus 4.9h all over h. My h's can cancel to 1, and what I'm left with is negative 19.6 minus 4.9h. And once again, we say the limit as h goes to 0. Well, this section over here, the negative 4.9, will also go to 0. So our limit would be equal to negative 19.6. And so what that means is that our rock would be falling at 19.6 meters per second after 2 seconds. All right, in this lesson, we explored rate of change. And we looked at a formula that allows us to find the slope of a tangent, as well as we learned about the normal to the tangent. Be sure to work the exercises that your teacher assigns, and we'll see you next time.